Hello everyone, and welcome back to your most favorite class ever. Of course, it is Algebra 1 taught by the inimitable Mrs. Weibel. We're going to be doing section 2.7, which is about sets and operations today. And you know that my trademark is these lame jokes that I start with. Well, see my book? Best riddle book ever. This was from a good friend who was a student of mine last year. It says, "Hi, Miss Betsy. Okay, so I wanted to give you something you could use every time we come to class or you do a video. You know, something useful that makes everyday life a little more fun and joy." So I now have some even lamer jokes to add to my collection. So for today, can you tell me, why doesn't a frog jump when it's sad? It's too unhappy. And how do you get extra frogs off your back window? Well, you use the rear window defrogger. So, now that you have had your daily groan, let's go ahead and talk about sets and operations. So all a set really is a collection of objects. You know, you have a set of silverware. You know, you'll have a 4-place setting so that you would have silverware enough that you put on the table so that you can have 4 people eat and have a knife, a fork, and a spoon apiece. So at its most basic description, a set is nothing but a collection of objects. But of course, mathematicians have had to come up with a way to describe those sets and special symbols to use for it. So you see that they have, it's called set builder notation, and they're going to use braces to identify a set. They might say something like, let's say the set of whole numbers. So the whole numbers, which is W, is that showing up down there? The whole set of numbers, which is W, can be described using set builder notation this way, where we have W is equal to the set, that's how you read that brace mark, the set that contains the elements 1, 2, 0, 1, 2, 3, and so forth. And you know that the ellipses here, these dots, means that this pattern continues on forever. And they just read the braces as the set of, or the set containing. The numbers that are inside this set are called the elements of the set. Yes? Okay, we'll go on with something else. And we have some more vocabulary that we're going to be talking about as well. We talk about the elements of the set. Let me make sure that I can get this. Didn't leave myself quite enough room with my picture. So, since I didn't do that and I worked so hard to draw you this pretty picture here, let me show you what I have going on here, and then we'll review by defining some of the elements of the set. First, we have this set here. You see right here in the middle, I have a 2, 4, and 6, and these are drawn in blue and green. So first we have this set C. And C is the set that contains the elements 1, 2, 3, 4, and 5. Anything that's written in blue. 1, 2, 3, 4, and 5. And then we also have set D over here, and D is the set that contains, I'm still fighting that laryngitis I had, I'm sorry. D is the set that contains the elements 2, 4, 6, 8, and 10. So we have 2, 4, 6, 8, and 10. And you'll notice that when I was describing these sets, I'm using some vocabulary. I'm using vocabulary that says the set that contains the elements. An element is just a piece that is inside the set. An element of your set of silverware would be a fork. And they use this funny looking symbol here. It's sort of like an E. So if I said 4 is an element of C, what this means here is that the number 4, the numeral 4, is contained in the collection of objects that we've decided to call C. Likewise, if we said 1 is not an element of D, they call this negating. When you slash through something, you negate it, you make it negative. This here says that number 1 is not an element of D. You can't find number 1 in that collection of objects that defines this group D. Right here we have the whole numbers. This is called an infinite set. And I bet you can tell me exactly why that is an infinite set. Well, of course, there's no end to it. The number of elements within this set is limitless. Well, if W is an infinite set, is C an infinite set? Is D an infinite set? Well, duh. Do the number of elements that are contained in those sets, can you never get to the end of them? Well, no. You simply have 5 elements in each set. So both of these sets are defined to be finite, which is the opposite of infinite. If infinite means that they cannot be contained, God is infinite. We cannot contain him. We can't put him into a box. We try really hard to force God to fit inside our box, but he just doesn't fit in our box because God is infinite. You cannot contain him. I think it's in the Gospel of John. John says at the end of his book, he says, there are many, many more things that Jesus did, and if we wrote down everything that he did, the world wouldn't even contain the books. The point being right there that there is so much more to God, so much more to everything that he would have us to do and to know in a relationship with his son Jesus. So it's infinite. It goes on forever. We are finite. We are very much limited by time and space in the years that God gives us. So we have finite sets, we have infinite sets, and we now have a very messy board. So let's erase some of these things because you've now learned what it means when we say something is an element. So we can get rid of 1 is not an element of D. We also saw what this is called set builder notation. Set builder. This is actually the beginnings of set builder notation. Would actually be the set of all W such that, continues on, that's really beyond where we are right now. So we have this, the set W contains the set of elements that follow the pattern 0, 1, 2, 3, and so forth. Forever. That's infinite. We have finite sets, which have a limited number of objects in them. And we've learned that a set is a collection of objects. So now, we're back down to this picture we have here. And this is where we talk about combining sets, where you put everybody together, you get a group and you say, okay, we've got a set of boys and we've got a set of girls. And we join everybody together. And that's the union of sets. So what we have right here is set C, which contains the elements 1, 2, 3, 4, 5. Set D, which contains the elements 2, 4, 6, 8. And if we put all of those together, let's just say that we put C plus D. Do not necessarily write this in your notes because C plus D is incorrect writing, but we're going to combine them together. So what do we have? We have 1, 2, 3, 4, 5, 6, 8, and 10. Now you'll notice we have a 2 in C and we have a 2 in D. I didn't write them twice. That's because I don't need to. It's redundant. Once you've said, I've got a 2, you don't need to say, I have a 2, I have a 2, I have a 2. It's sort of like the little child that says, Mommy, 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 Mommy. You only have to say Mommy once. You only have to say 2 once. So if we combine these sets, just like we did here, this is a combination of both sets. And look at what we have. 1, 2, 3, 4, 5, 6, 8, and 10. 1, 2, 3, 4, 5, 6, 8, and 10. We didn't make any duplicates of the elements of the set. Well, in set notation and Venn diagrams, we do not say C plus D. We say C union D. C union D. That's not code. You know, there's something that's a little different about how you do the U. I can't distinguish it. But the U is union. And the upside down U, it sort of looks like a croquet wicket. And I don't know how many of you have ever played croquet. But it's an arch. That's the intersection of two sets. So the union of two sets is like a cup that's holding everything in. We have the union of set C and the union of set D. And that's every single item that is contained in the set. Now if you have the intersection of C and D, C intersect D, you're going to have 2, 4, and 6, because what you're looking for, I said 6, and I must have written my sets down incorrectly. Yeah, because you say I have the blue is 6. So C actually contains this extra element. It has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So we're looking for the elements that occur in both of these sets. It's sort of like finding greatest common factor. Least common multiple. We have a 2. And we have a 4. And we have a 6. Those elements occur in common. So that's where the intersection is. It's like if you have this road going one way and this road going one place, the only place where those roads, where their concrete is the same, is right there at the intersection, which is what we have illustrated here with our picture. Some of you have had experience and exposure to this type of a picture. This is called a Venn diagram. What a Venn diagram is, it's a collection of circles that are overlapping that show how different sets relate to one another. You look at this one and you have the set C, which I erased from up here, but I had C was blue, 1, 2, 3, 4, 5, and the set D was green, 2, 4, 6, 8, 10. So, if we wanted to do the union of those sets, remember the union is the cup, you know, it's that U-shaped thing, holds everything. The union of that, marker, would be everything that occurs in set C. All of this blue area here. That's set C. And then we also have everything from set D. So the union, as we show the picture of this on a Venn diagram, where I put my, is all of the blue, 1, 2, 3, 4, 5, 6, and all of the green, 2, 4, 6, 8, 10. The intersection is the place where they overlap. And you can see right here, we have the blue is hitting here in the middle, this way. And you have the green hitting here in the middle. Just like when I drew these numbers to begin with, and I had the 2 drawn in blue and green, I had the 4 drawn in blue and green, and I had the 6 drawn in blue and green. So the intersection, the area where they overlap, the intersection contains only those elements that you find in both of the sets. So this is basically what we have with union and with intersection and with talking about finite sets, with talking about infinite sets. So that's all I'm going to talk about for right now for section 2.1. I'm going to call this part 1. I'm going to do another tape where we talk about subsets and I do a couple of examples for you.